Okay, so I was reading this Nature paper a couple months back, and it was going great until I saw this monstrosity. And to hopefully help others avoid the confusion that I had, I've decided to make this video as a visualization for how ROC curves really work and why they matter, with the key insight being that they tell us how well a classification model can distinguish between two states. Let's say you're a doctor and you want to see how effective a new test is at verifying that a patient has a virus. Well, you might approach this by taking some sample size of patients and then juxtapose if they truly had the disease with the readings of the test. But real-world testing is imperfect. We have to consider that we could have instances where the patient didn't have the virus, but the test came back positive, as well as cases where the patient did have the virus, but the test came back negative. An ideal test would maximize both correctly identifying those with the virus and those without the virus. So how exactly can we tell how good of a classification model we have? Let's group our data into truly positive and truly negative cases. With a large enough sample size, these groups typically follow normal distributions. And if we plot these points on an axis scaling to the probability we think a certain test result will come back positive, we end up with two overlapping distributions that show where our positive and negative readings could fall. If we're clever, we could add a line, let's call it our threshold line, where we will only look at values to the right. The farther we slide this threshold to the right, the more we avoid false positives in our sample. At any point, we could measure the true positive rate, being the positives to the right compared to the total number of positive readings, and our false positive rate, being the negatives to the right compared to the total number of negative readings. And then, we could slide along our threshold value to find the true and false positive rates for any predicted probability. A better way to visualize the threshold line might be to revisit our original classification approach. Notice that we are already establishing a cutoff point to determine which experimental test results should be considered positive. The threshold line is essentially just a rescaled version of this cutoff, telling us the level of certainty we can have to classify a given data point as a positive result. When we plot the calculated rates relative to one another, and then continue to slide the threshold, what we're left with is a tracing of the ROC curve. Let's consider a different test where the means of the distributions are closer to one another. The change we've made means that the calculated true and false positive rates end up being much closer to one another, and the result is that the ROC curve ends up being a lot closer to that diagonal line. We'll get back to that in just a second. Okay, that's all great, but why again should we even care about ROC curves? Well, the simple answer is that the area under the curve tells us how good our model is at finding the distinction between two states. In fact, let's take a look at three different models with varying separations between states. This is also known as discriminability. An ideal model would keep its states as separate as possible, and an increased area under the curve reflects this increased distinction between states. In a special case with no distinction, we're left with a diagonal line with no area under it. This is also known as a random classifier because the model performs no better than a random guess. And that's just about it. Put simply, the area under the curve tells us exactly how separate our two states are and how much they overlap. Thanks much, and goodbye.